Enamel, the non-living outer coating of teeth, was the model for a rigid and durable new material developed by Michigan engineering researchers. Consider the computer chips that run autopilot on a passenger jet, or the electronics driving our ever more intelligent cars. Both need to be made out of strong, rigid materials. But in order to last, these materials must also handle frequent vibrations without cracking. That's why DARPA, the Defense Advanced Research Projects Agency, challenged researchers to come up with such a material. Nicolasa Котова, a professor of chemical engineering at the University of Michigan, came up with a novel solution, which was first inspired by the bone of a cuttlefish he found along the Spanish shoreline. When Котова examined the cuttlefish bone under a microscope, he saw layers of vertical, column-like structures. Having never seen this before, he looked for organs with similar structures from other creatures. When he got to studying the teeth of various species, like from a tyrannosaurus, an ancient walrus, and even his own wisdom tooth, he saw something remarkable.
I was amazed. I really could not believe initially how consistent the structure of the teeth is from totally different creatures, from totally different epochs and eras. And I initially thought it's a mistake because I knew how variable all the other organs are.
The enamel was oddly similar across all species past or present. Nature was clearly onto something. It turns out the structure of the enamel is strong enough for tearing into meat or biting through mollusk shells, but it also can endure a lifetime of frequent vibrations from chewing and other shocks.
When I looked at the teeth enamel, I saw the material which is organized by the pillars of inorganic materials which are interlaced with some soft organic matter.
And actually, the tight bond between the ceramic pillar-like structures and the soft matter, a protein matrix, is crucial to its longevity. When the ceramic columns bend under pressure from above, the strong friction between it and the softer proteins dissipates the energy, minimizing the risk of deterioration.
And I tried to replicate it in some different formats, and it was actually quite hard. When you need to grow the crystalline structure from the substrate up, and in the same time interface it with the soft polymeric material, that encounters quite a lot of chemical fundamental problems.
Котова and his team eventually found a way to grow a sheet of this artificial enamel. Because of its structure and how it's developed, they were able to further build up their new material layer by layer to get the desired thickness. Compared with other materials with similar properties, Kotova's enamel is lighter and more effective. The next step will be making it easier to produce.
Now we know how to create the material which would be resistant to long-term vibrations, resistant to aging. But how to make it in a large scale? For instance, for electronics or for cars, not just for implants, not just for some one-off devices, but something that we can use in a massive scale.
Scaling up will require a long and challenging effort from both academia and industry, but Kotov believes this new material will have many successful applications in the future.